Today I'd like to talk about how to measure the size of an infinite dimensional vector space. You might say, well, why would we need to even think about an infinite dimensional vector space? Our world is only three-dimensional, or maybe four-dimensional if you include time. Well, it turns out that a lot of very interesting vector spaces are infinite dimensional. So polynomial vector spaces are infinite dimensional. Maybe those are polynomial vector spaces in one variable, two variables, or even infinitely many variables. Exterior algebra vector spaces are interesting. So remember that those are polynomial vector spaces where the variables do not commute. You get anti-commuting. And then maybe even like the space of all smooth functions from R to R, that's also an infinite dimensional vector space. And all of these like various algebraic objects that I've talked about are really simple cases of things you might find in mathematical physics. Some more things would be like Kac-Moody-Lie algebras or vertex operator algebras or so on and so forth. So needless to say, it's pretty important to think about infinite dimensional vector spaces, and so we should think about how to measure them. And the way to start thinking about that is via the following definition. So a vector space V is said to be Z-graded or integer graded if we can decompose it into a direct sum of subspaces indexed by the integers. So we have V as the direct sum over n integers of V sub n, where we say that V sub n is the nth graded component. And then if we've got a vector V in this nth graded component, we would say that its weight is equal to n, or sometimes its degree. Kind of the word that we use there varies depending on context, but I'll just write WT of V equals n. Okay, so let's jump into some examples. So for our first example, we'll look at just the polynomial algebra with one variable. And so let's note that we can very easily write down a basis for this polynomial algebra of just monomials. So the basis would be made up of the number 1, x squared, x cubed, x to the fourth, and so on and so forth. Or if we wanted to put this all together, we would write this as the monomials x to the n, where n runs over all non-negative integers, like that. And then we've got to decide on a grading. And I think maybe the obvious thing to do would be to say that the weight of x to the n is equal to n. Now, this is a really important thing that I'd like to point out, is that the weight of a non-homogeneous element doesn't make any sense. So if we were to say, try to find the weight of x squared plus x to the fifth, well, this kind of question doesn't really make sense because x squared is weight 2 and x to the fifth is weight 5. And in this particular setting, we're thinking about just homogeneous grading. So like I said, we don't consider something like that. Okay, so how can we decompose this using this idea? Well, that would be as the direct sum, as n goes from 0 up to infinity, of c times x to the n, where we're thinking about c times x to the n as just maybe alpha x to the n, as alpha runs through all complex numbers. So something like that. Okay, so let's maybe boost this up just a little bit to something with two variables. So let's say we've got c adjoin xy. So that's going to be polynomials in two variables. So let's write that down in x and y. We'd probably like to grade this similarly as to kind of above. Maybe we would say the weight of x to the a, y to the b is equal to a plus b. That would be maybe an obvious way to do it. And then we could say that the nth graded component here, which I'll denote by c adjoin xy, maybe underscore n, so that's going to be all x to the a, y to the b, such that a plus b equals n. So now these graded components are larger than one-dimensional, which is different than what we have in our first example. Notice that those are all one-dimensional. So for instance, we have like something of the form 3x squared plus 2xy squared, maybe minus 5y cubed. Something like this will have weight equal to 3. And notice that's not a monomial, but each of these monomials themselves are weight 3. So like I said, this is not one-dimensional in this case. Okay, so now that we've got an idea for how this kind of definition of a graded vector space works, let's maybe move on to the measurement of an infinite dimensional vector space using this grading. So moving on to our next definition, let's say that we've got a graded vector space, a z-graded vector space, like the examples we just looked at. We define its graded dimension as follows, and this is the measurement I was talking about. So I'll denote it by dim q of v. So it's like the q dimension, if you will. And that's going to be the sum over all integers of the dimension of the nth graded component times q to the n. So I'd like to point out that this only makes sense if the dimension of each of the graded components is finite. And so that's something that generally happens in this setup. Although there's some tweaks that you could do with multi-grading if you get infinite dimensional components. Now, I'd like to point out that in the language of combinatorics, this graded dimension is in fact a generating function for the dimension of the nth graded component. Okay, so let's look at what we've got here. So this was the example we looked at before. So we've got our C adjoin X, our polynomial algebra with one variable. And here we know that each component is one dimensional. So if we were to do the dimension, the q dimension of C adjoin X, we would get the number 1 plus q to the 1 plus q squared plus q cubed plus q to the 4th plus dot dot dot. And we know it'll be this because, like I said, each of the graded components is one-dimensional. So that gives us a coefficient of 1 in front of all of these things. So the first grading component is one-dimensional. It's spanned by just x to the first power. The second graded component is one-dimensional. It's spanned by x squared, and then so on and so forth. And so this would be our q dimension, just this geometric series, if you will. And generally what we'd like to do here is to simplify this into a rational function if possible. And we use geometric series summing tricks or whatever to do that. So notice that this is going to be 1 over 1 minus q. And that's how you would, like I said, generally write down the q dimension or the graded dimension for this polynomial algebra. Okay, as this summed geometric series, where we take q to be a formal variable, so we don't really worry about places where it's convergent. Okay, so let's look at the start of another example. So let's say we look at C adjoin x, y. And let's say we have that same grading that we had before. So the weight of x to the a, y to the b is equal to a plus b. Now, let's maybe say n and then a basis for C adjoin xy sub n, so the nth graded component, and then we'll have the dimension of, I'll just write it as Vn here to make a little bit of a chart. We won't go so far, we'll just go a little bit. So here, let's say n equals 0, so the basis would just be the number 1, so the dimension is 1. So let's go n equals 1. So our basis will be x and y, so our dimension is 2. Then let's go to 2. So notice our basis will be x squared, xy, and y squared, so the dimension is 3. And I think you can see where we're going here. So notice if n equals 3, we get x cubed, x squared y, xy squared, and y cubed, so the dimension will be 4. So in fact, for n equals n, the dimension will be n plus 1. So we could write that over here. The dimension of v sub n will be n plus 1. So that tells us that the graded dimension, or the q dimension of C adjoin xy, will be the sum as n goes from 0 up to infinity of n plus 1 times q to the n. Okay, so now let's maybe clear off enough room so that we can find a closed form for this graded dimension. So here's what we determined on the last board. The graded dimension for our two variable polynomial algebra was this sum as n goes from 0 to infinity of n plus 1 q to the n. You can write down a basis for the nth graded component pretty easily. It goes from x to the n, y to the 0, up to x to the 0, y to the n. So that clearly counts n plus 1 objects. Okay, but now we'd like to find a closed form, and we can do this using geometric series summing trick again. So let's start by reindexing this. So we'll reindex this by sending n to n minus 1. So that means this will start at 1 and go to infinity now. And then we'll have n times q to the n minus 1. But that looks exactly like the derivative with respect to q of the sum as n goes from 0 to infinity of q to the n, just using the power rule. But that's going to give us the derivative with respect to q of 1 over 1 minus q using geometric series trick. But in the end, let's see, that's going to give us 1 over 1 minus q quantity squared. And again, that's just using like standard derivative rules. Okay, so now we're going to look at a couple more examples. So our next example is a really important polynomial algebra of infinitely many variables. So I'll index those variables x1, x2, x3, so on and so forth. And I'll make my grading a little bit differently than I did before. I'll say that the weight of the monomial x1 to the m1, x2 to the m2, all the way up to xk to the mk is equal to m1 plus 2m2 all the way up to kmk. So that means that the monomial x1 has weight 1, the monomial x2 has weight 2, and so on and so forth. So in general, the monomial xn has weight in itself. So if we were to look at the fourth graded component, we could find its basis pretty easily. It's the basis of the following monomials. We have x1 to the fourth, x1 squared, x2, x2 squared, x1, x3, and x4. And you might notice that these are exactly related to the integer partitions of 4. I've made some videos on integer partitions in the past. So this is related to the integer partition 1 plus 1 plus 1 plus 1, because we have 4 copies of x1. Whereas this one right here is related to the integer partition 1 plus 1 plus 2. This guy right here, 2 plus 2. This guy right here is like 1 plus 3. And this one right here is 4. And so there are exactly 5 partitions of the number 4, and that's what we're getting here. So in fact, if you took v sub n, so I guess we're assuming that this is equal to v, well, then we could write its basis as x1 to the m1 all the way up to xk to the mk, where m1 plus 2m2 plus up to kmk equals n. So something like that. So how many guys are in here? So the dimension of Vn, well, that's going to be exactly the number of partitions of the number n. Just as we saw right here, the dimension of V4 was 5. That's the number of partitions of the number 4. So here we could say Pn, so this is number partitions of n. So putting this all together, we see that the graded dimension, so the q dimension of this infinite dimensional polynomial algebra, is given by the sum as n goes from 0 to infinity of p of n q to the n, where, like I said, p of n is the number of partitions. And in some previous videos, we calculated this generating function, and it turns out to be this nice infinite product. So it's the product as m goes from 1 to infinity of 1 over 1 minus q to the m. We could write that out as 1 over 1 minus q times 1 over 1 minus q squared times 1 over 1 minus q cubed, and so on and so forth. So how to read this in terms of our variables here, you think that this 1 minus q term in the denominator is kind of connected to this weight 1 generator x1. Whereas this 1 minus q squared term is connected to this weight 2 generator x2, and so on and so forth. So this 1 minus q cubed term is related to this weight 3 generator x3. Okay, so that's looking nice. Okay, so now let's look at another example of this. So our next example will be like an odd version of what we just saw with our infinite dimensional polynomial algebra, and that's an infinite variable Grossman algebra or exterior algebra. So let's recall that that's essentially just a polynomial algebra where we call the variables thetas instead of x's, and we have anti-commutativity instead of commutativity. So theta I, theta j is minus theta j, theta I. And that has the really important repercussion of theta I squared is equal to 0 for all I. That's because it will be its negative. So just as an example, let's look at the basis of the 7th graded component, where we're taking the grading similarly as before. So the weight of theta m is m. So note that we cannot repeat any of the thetas because of this rule right here. So we would take as a basis theta 1, theta 2, theta 4. So notice that adds up to 7. Theta 1, theta 6, theta 2, theta 5, theta 3, theta 4, and theta 7. So there's no other way to do this. You can't get a quartic term here because 7 is not like big enough to allow for a quartic term. So let's see, this has dimension 1, 2, 3, 4, 5 again, even though we have v sub 7 instead of v sub 4. And these, again, are related to partitions of 7. This guy right here would be the partition 1 plus 2 plus 4. This one would be 1 plus 6. This one would be 2 plus 5. This one would be 3 plus 4. And then finally, this last one here would be 7. So we have something like partitions of 7 again, but now it's partitions of 7 where we can't use any of the parts more than once, because using a part more than once would correspond to having something like this purple underline term, which would give us 0. So that gives us some motivation to write down the graded dimension of this algebra pretty easily. So the graded dimension of this will be the sum, as n goes from 0 to infinity, of, I'll say p distinct, so I'll just put dist for distinct, of n q to the n, where that's the number of partitions of n into distinct parts. But I think we did this in a previous video as well, and we calculate that the number of partitions of n into distinct parts looks like this. 1 plus q times 1 plus q squared plus 1 plus q cubed, and so on and so forth, which ended up being the product as m goes from 1 to infinity of 1 plus q to the n. And this actually has a relation to the number of partitions into odd parts, if you remember that as well. Okay, so let's maybe make a quick summary as well as like some bonus information, which we won't quite cover. So let's finish this off with a nice summary. So our infinite variable polynomial algebra in even or commuting variables had the following graded dimension. So it was related to the number of partitions, unrestricted partitions. And then for odd or anti-commuting variables, it was the number of partitions where we only had distinct parts. Now, in terms of mathematical physics, this first algebra is related to bosonic algebras or bosons, whereas this second algebra is related to fermionic algebras or fermions. Although a lot more stuff is happening kind of in the background there. And then just as some extra information about these graded dimensions and stuff, if you take this infinite variable polynomial algebra and quotient out by a certain kind of nice ideal, you get, well, it's the same thing as the infinite jet scheme of a single variable polynomial kind of at a squared point, and they're both related to the Rogers-Ramanujan identities. So in other words, if you take the graded dimension, you get something that looks like, well, it essentially is one side of a Rogers-Ramanujan identity. And that's a good place to stop.